Welcome back. So we're ready to start our afternoon session. And our first speaker for the afternoon is Graham Neubig, who is a faculty member at CMU and also the founder and CEO of OpenHands. Is that correct?
Chief scientist.
Chief scientist,
yes.
At OpenHands. And so he's going to tell us about some of these lessons from the trenches about working with AI coding agents that people actually use out in the real world. So very excited to have you here. Thanks for joining us.
Yeah, thanks a lot for having me. And yeah, so I'd like to give a very practical talk, but also show how some of the practical problems that we encounter when building coding agents can be transferred into research and maybe even further formalized for the people here who are thinking about these sorts of things. But my motivation for working on agents for software development in the first place was actually very related to what Armando mentioned in the morning, which is that software is not built for the purpose of being software. It's built for the purpose of solving real-world problems. And this is kind of encapsulated in this now rather old quote from 15 years ago by Mark Andreessen, where he said, more and more major businesses and industries are being run on software and delivered as online services, from movies to agriculture to national defense. Over the next 10 years, I expect many more industries to be disrupted by software. And this, of course, in fact, happened 15 years later. Now much of our life runs on software. And so my underlying idea is if we give everybody the ability to quickly write software to achieve their goals, you could think of all the wonderful things we could accomplish. And that includes both software developers, of course, but also people who are not software developers. Some examples of this are the Nobel Prizes in 2024 from physics and chemistry. And these were given not to people who were running large-scale particle accelerators at CERN or running wet labs, but rather given to Hobfield and Hinton, who invented machinery for neural networks, which then were able to contribute to physics. And then Demis Hassabis, for instance, from DeepMind, who came up with methods using software to uncover essentially things related to protein structure prediction. If we look at a slightly old graph of my personal transition in using AI for code, this was my commits to GitHub, or my PRs that were merged in GitHub. The blue ones are the ones that did not have an agent as a co-author, or at least did not have an agent listed as a co-author. And the red ones were ones that did have an agent listed as a sole author or co-author. And you can notice a few things from this graph. The first thing is that professors are busy during the school year, and they don't have a lot of time to code. And so my contributions from September to May were rather sparse in 2023. But when I switched over to using coding agents, both the number of contributions that I made grew significantly. And as coding agents got better, I gradually transitioned to writing essentially all of my code through coding agents. And this oldest one is from August, or the newest one is from August 2025, because that's when I originally created this graph. But I assume that this trend continues based on my intuition. And the coding agent in particular that I'm involved with is OpenHands. It's one of the biggest open source coding agents. It's fully open source, MIT licensed. We also have a startup around it. I am not the CEO of the startup, but our CEO, Robert, is here. He's actually based in Boston, so I'm happy to be part of the Boston community. And I'd like to show just a little bit about what the agent looks like. Basically, this is our online version where we have it running in the cloud with sandboxes where it can work inside the cloud. And I can do things like, say, tell me information about the MIT AI encoding event that is happening today, and create a site that features all of the speakers along with their biographies and profile photos, which would work if my speech recognition did not just fail. So tell me about the MIT AI and Coding event today and create a site with all of the speakers and their profile photos. So this is just one example. This is like a greenfield app creation example where it's a combination of information gathering and greenfield app creation, where essentially we are searching the web. And so we can see the agent search the web for AI workshop on AI and coding, January 23rd, 2026, getting more details from the website. And then it will go in and, ideally, find all the speakers, find their profile photos, create a site, and stuff like that. So, of course, it can do lots of other things. Like, it's also used for kind of actual enterprise software development tasks, like going in and upgrading existing code bases, implementing features, fixing bugs. We also recently use it a lot to debug when something goes wrong on our web service. So if we get a complaint from a user, we'll ask it to go in and read the logs and diagnose where the problem is happening in the code base and fix things. So these are, it's pretty diverse. We started working on this about almost 2 years ago now. I think we started in March 2024. And I've learned a lot of stuff since then in making agents actually work. And I'd like to share a little bit about each of these and also highlight some research work that we've done to resolve them. And then at the end, I'd like to talk about some research problems that we're worrying about now. There are things that are like the things that if you're working on AI and code, I'd love to have a solution for, so please fix them and then tell me what you did. So the first lesson is believe in simplicity. And we talked a little bit about SWE-bench this morning, but SWE-bench is kind of one of the typical benchmarks for software development with agents. And it involves taking open source repositories, setting the repository state to the state at which it was when an issue was filed on that repository, and then trying to fix that issue. And then we test whether the agent was successful at fixing the issue by whether the tests that were introduced together with the issue pass. So if you've heard of SWE-bench and didn't know what it did, that's what it does. Another important note is that this is only Python, and it's only on open source repositories. So maybe a good way to think about it is not, is AI good at software engineering, but rather is AI good at solving Python bugs on open source projects. But what we can see is this was released late 2024 last year, or at least the first numbers were reported on it in 2 years ago, sorry. And the numbers have gone up in fits and starts. So they essentially go up really rapidly, and then they level off for a while. They go up really rapidly and then level off for a while and things like this. And can anyone guess why they typically go up very rapidly? Any ideas? Yeah? Yeah, a new language model comes out. So one of the things we've noticed is that having a very powerful language model behind your agent is really important. And to give a bit of context, this was not obvious a year ago. And there were a number of different ways of building agents. And this is an example from another work, which I will pick on just a little bit, called MetaGPT. And basically, they said, we need to have a software company agent. And then the software company agent has a boss agent. And then there's a product manager agent, and an architect agent, and a project manager agent, an engineer agent, and a QA agent. So the software company agent comes up with the idea, it comes up with the environment, and all of the other things. And this might seem like a good idea, because that's how a human software company actually works. But part of the reason why a human software company works that way is because there are some bosses who are really good at being a boss. There are also some bosses that are, really good, or some people who are really good at being a product manager, and some people who are really good at coding and things like this. But I think one thing that we've realized is that language models, to a greater or lesser extent, but I would argue largely, have the ability to do all of these things pretty well if you provide them with the appropriate instructions. And so instead, in OpenHands, the architecture that we've largely taken is we have an agent, and that's it. That agent does all of the jobs. What we do have is we have something called skills, which we introduced a bit before, but now Claude Code also has introduced, and it's kind of become a standard where you can pull in individual pieces of knowledge into any agent at any time, but it's not like, okay, you have this agent, then you have this agent, then you have this agent. It's rather like, okay, you have one agent, and then you provide it with individual skills, and you also provide it with the tools it needs. So then the question is, what tools do you need to do a pretty good job at a pretty broad variety of tasks? And so we had a paper where we actually examined this question and tried to come up with a very small set of tools that nonetheless would allow you to do very general things. And the paper is called Coding Agents with Multimodal Browsing are Generalist Problem Solvers, if you'd like to take a look at the actual results. But this is also what's behind our default tool set in OpenHands on the OpenHands Cloud, for instance. So number one, the first tool is bash. So it can run commands in the bash terminal. We actually also, in addition to this, give it the ability to run Python programs in a Jupyter notebook style thing, and that's useful for data science tasks, but arguably you don't really need that. You could probably remove this and still do a good job. The second one is a file editor, and the file editor, basically what it allows you to do is it allows you to edit lines in files. The reason why we think this is important is because human programmers also have a file editor, right? It's called their IDE, and they go in and they edit files manually. So we need an equivalent to this for the agent to do its work well. Arguably, you could remove this and let it just edit files with bash commands, but there are some finicky things about this, like it might read a really large file and crash the large language model's context window and other things like this. So we found a special purpose file editor does still manage to help. Finally, we gave it two tools. We gave it the ability to use a web browser. And the web browser serves essentially it serves two purposes. It allows you to read information online. It also allows you to access visual information. So if you want to read a plot in a paper, or you want to read a PDF or something like that, you can use a web browser to do that too. And so this allows you to handle things multimodally. And then finally, you could use your web browser and go to Google, but practically then Google will block you and start putting up CAPTCHAs, and your agent will refuse to do the CAPTCHAs. So we also provide it with an API to search the web. And so these are basically all the tools we provide by default. And once we've done this, you already have tools to do most of the rest of what you need. So if you look at all of the Python libraries, there's Python libraries to do virtually everything. You can do numerical optimization, you can do plotting, you can do all of these other things. And so this small set of tools is also the tools that we have that a lot of human programmers use. And so once we have these, we can do a pretty broad variety. And so, of course, we actually evaluated this in the paper, and we demonstrated that this, at the time, beat the state of the art on 3 benchmarks on information gathering, kind of like general purpose agents, and also multimodal programming. I think it also ideally should have created the schedule here for the AI encoding workshop. And you can compare this to the actual AI encoding workshop page and tell me which one you like. But I think it did maybe a pretty good job here. So this was enabled. I'd like to go back to my slides. This was enabled by the search API, where it searched the information, the visual browser, where it looked at and confirmed that the site was actually working, the code editor, where it ran the code, and the bash, where it where it actually brought up the server and did other stuff like that. The next lesson that I'd like to go into is code don't click except at a last resort. This is based on a paper we have called Beyond Browsing API-based Web Agents. And there's essentially kind of a dichotomy in the agent building community right now, and especially maybe 6 months ago, where there was an idea that agents will either be operating and interacting with the world through user interfaces that were created for humans or through code. Maybe some people would say both. The argument for interacting through user interfaces was, well, humans interact through user interfaces, so if we match that, we'll be able to do anything that humans do. There's a problem with this, though, which is that actually it's pretty inefficient to do things through a user interface if you can write code effectively. And I'm sure if you're a programmer, you have encountered this where you were stuck using a user interface where you wished you could write a for loop to do some sort of repetitive task. And so this is illustrated by this figure here where we took an example from a data set called Web Arena, where Web Arena essentially was a data set that was created to test whether agents could interact with the web. And we asked a web browsing agent to solve a problem, which is open the latest commit log by the user Amy that has a failing test. And what the agent did is it went to github.com, it searched for the user Amy, it clicked on the user, clicked on the repository, clicked on sort by last updated, clicked the last updated repo to find whether there was a failing test, and then it continued clicking until it ran out of turns and failed the task. In contrast, a coding agent, which was allowed to interact with the API for the website, was able to basically solve it in one shot. The problem is not all websites have good APIs. And so in some cases, you need a hybrid approach. And so that kind of informed our way of doing things where you can ask the coding agent to use an API if it can, and then interact with a website if it must. And we have some interesting results in the paper. But basically, what you can see is on some websites, if we took the web browsing agent, it did quite poorly. But if we gave it an API, it got 3 times the success rate of the other agents, which is true for the GitLab and map examples. But on other websites, it was comparable or even worse, such as these websites here. And the reason for this was essentially just the quality of the APIs on the websites. And so you can see if the websites are poor, the API-based agent does poorly. If the APIs are good, the agent does well. But we also have the hybrid agent that can do both, and that was kind of like strictly better than the other ones. Another interesting thing that we did was we did a causal intervention on the quality of the Reddit API, where we just added, I guess, 13 more endpoints to cover some of the more common failure cases, and that doubled the accuracy on Reddit. And so what does this mean? This means essentially, if we have a good API, we can largely rely on coding agents in an API. We don't need to go through a GUI. I would like to note that this work came before MCP was a thing. So if you're familiar with MCP, it's a very popular way of providing tools to agents. And now kind of all of these websites that people are using either are providing an API or an MCP to allow agents to interact with them more. So I think that kind of like validates this hypothesis. So lesson 3 is agentic training is essential. I kind of alluded to this in the first part of my talk where I demonstrated that we had large gains in new language model releases. And these new language model releases don't just happen, right? There's people at language modeling companies working very hard to make their language models very good. They won't tell you what they do, because they want to earn lots of money and not have other people steal their secrets. But I can tell you more or less what I think they're doing, and I'm pretty sure that this is one major element of what they're doing. So before I get into that, I'd like to talk about what makes a good agentic language model in the first place, according to my personal prejudices. But basically, number 1, a really good instruction following ability. So if you give a language model an instruction, it must be able to accurately do the things you asked, accurately not do the things you told it not to do. In addition to this, agentic trajectories become very, very long. So even when you have a lot of intervening context, when you have multiple comments within a single trajectory, it needs to be able to appropriately prioritize them. When a user says, no, don't do that, do this, it needs to understand what that is and understand what this is and, appropriately contextualize. So this is a very non-trivial problem, and it's actually a big discriminator between the really, really good models and the moderately good models. Another one is tool use and coding abilities. So it needs to be able to write code in whatever language you want it to write it in. It also needs to be able to use tools, and that's a little bit different from writing code in that tools are often added on the fly. And it's you give it a tool description and say, this is how you use a web browser, call these APIs to use a web browser. It needs to be able to appropriately follow those. Another thing is it needs to have environment understanding. So if you're going to have it do front-end programming, it needs to be able to understand all of the things in the front end and understand when the design is good versus when the design is bad, when something is broken or not formatted properly. It also needs to have error awareness and recovery ability. So if it fails at doing something, a very common failure pattern that you see in weaker language models is that they'll keep on doing it over and over again and expect it to work the third time they tried it, which, of course, no good human programmer would do. Finally, reasonable cost. And I think arguably we're getting to the place where we have language models that can do all of these things, but the best language models are still pretty expensive if you're using them 24/7 with 4 language models or 4 agents running at once. So in order to do training, you need to have data. And there's basically 3 major ways to get this data. The first way to get this data is through rollouts. And rollouts are basically an element that you perform in reinforcement learning where you have an input to the model, the agent. The agent is allowed to act in its environment. And then after it acts in its environment, you have a reward at the end, or maybe even an intermediate reward while the agent is acting. And so here we have an example from SWE-GYM, which is a training environment that we created for SWE bench-like problems. It was probably the first reinforcement learning environment for kind of coding agents back in the ancient history of 2024. My history time span is much shorter than Armando's history time span, unfortunately. The training example, basically, it looks similar to an example that we have in SWE-bench, where we have an issue and a code base, and then our reward is derived from whether the agent is able to create a pull request that passes all of the unit tests based on this issue. Once we do this, we can get a gradient update to update the LLM-based agent using reinforcement learning. Another alternative thing we can do is we can do filtered fine-tuning, where basically we take all of the positive examples, we add them, we take all of the examples that didn't pass the unit test, and we throw them out, and then we can train based on that. A second major method for creating this data is synthetic data. And there's a lot of methods on this, but I would like to highlight our method, specifically GoBrowse. And we examined this from the point of view of browser agents, but the general principles apply in other settings as well. So the way this works is it's inspired by a previous work in reinforcement learning called GoExplore, which does a pretty similar thing. We have an outer loop where we essentially have the agent explore the web page and identify pages on which it could perform tasks. Then we have a language model come up with tasks that could be done on that web page. We then ask the agent to perform the task on the web page. And then we have a language model as a judge to determine whether the tasks were executed properly, essentially. So this allows us to create trajectories where we explore to the proper page, perform a task on the page, and then we can add those to training data only if the LLM as a judge said it did a good job. So this is kind of standard way of doing things. There's other previous works like Bagel from Stanford that does stuff like this, and NetNav. But the thing that we added on top of this was we find the path to the initial state that we found in the outer loop iteration, and then we make further steps. So we step further into the website and come up with more complex tasks. And the idea why this is kind of interesting is you can also apply this to, for example, programming tasks where you have a multi-step thing where you need to do this, and then do this, and then do this, and then do this. And this could be applied there as well, although we haven't done that yet. So The idea is that this would allow you to come up with complex but high-quality training data. And of course, the results from this are good. So the final example is from human demonstrations. So if you can somehow convince lots of humans to do the task that you would like to do, this is another way to create data. I'm highlighting this paper that is notably not by us. It's by Google, where they had people use a lot of Android apps and recorded how they were using Android apps. They got 689,000 multi-step demonstrations by just asking lots and lots of people to do tasks on Android. Why was this not done by us? Because we don't have users to do 689,000 tasks on Android apps. So this is definitely very expensive. But if you have highly skilled workers or like people who can create this data for you, then this is another alternative way to do this. But one of the big takeaways is there's actually a lot of data out there that has been created in the past for training agentic models. But unfortunately, up until very recently, it was all in these very disparate formats, not easy to discover, not easy to use for training. A recent work that we did called the Agent Data Protocol is an attempt to fix this. And this was done together with CMU and OpenHands. And basically what we did was we took all of this raw data from all of these disparate formats, and we tried to come up with a minimal schema that would be expressive enough to be useful, but not so fine-grained and detailed that we would lose the ability to characterize, easily characterize existing data sets. And so this is kind of like what we called it is an interlingua, kind of inspired from very old work in machine translation, where once we convert things into a schema that, into the Agent Data Protocol schema, we can then take the Agent Data Protocol formatted data and convert it into the tool set and format that any downstream agent expects. And so we also have a way to convert into things that are useful for the OpenHands agent or the SWE agent or the Agent Lab agent. This was a lot of work. There's like 20 to 25 authors on this paper because we had to have a lot of people go in and actually, number one, come up with the protocol, number two, curate the data into this format. But the good news is we now have a data set that I think has about 3.7 million agent trajectories. So it's the largest data set for training agents at the moment. And we've demonstrated that you can train on this and come up with agents that are kind of generally good at a broad variety of tasks. So another thing that I'd like to talk about is benchmarking. And I talked a little bit about SWEbench. And one thing you'll notice on SWEbench is that the scores on SWEbench have gone up very quickly. There's a lot of language models that are very good at SWEbench, but the numbers are all on the leaderboard between like 70 and 75% if you use the same agentic harness. It's like not very differentiating between which of the language models are actually good or not. But on the other hand, similarly to the Agent Data Protocol, there are a lot of benchmarks that have been proposed. And they have not been necessarily standardized. So one of the things that we did at OpenHands was create a benchmark suite called VersaBench. And basically what this is this is our opinionated idea of some benchmarks that are useful for measuring progress on more broad software engineering applicability. And we've evaluated with respect to both this and with both accuracy and cost on this data set. So we have SWEbench, of course, which we've talked about before, but there's also ones on fixing failing builds, gathering information, building apps from scratch, doing front-end development, doing kind of general work-related tasks within a corporate environment, software testing, doing multilingual issue resolution in different languages like Java and C++ and Rust and other things like this. I kind of wanted to announce this here today, but we didn't quite make it in time. But next week, I hope, we'll be introducing a new version of this called the OpenHands Index, where we've kind of narrowed this down a little bit more and evaluated a lot of the more recent language models on all of these data sets. And we have some very interesting results. I'd be happy to talk about them in the discussion. But long story short, all of the language models are good at SWEbench. The real differentiation comes when you test the language models on all the other ones. And so, there's a big gap in how generalizable the various language models are to tasks that are outside of just Python bug fixing. Another thing that I've been thinking about a lot is we actually run a service that a lot of people use, and we'd like to be able to tell whether the agents are actually working for people. And so we have a paper done by one of our summer interns, Valerie, called on evaluating with humans in the loop. And basically what we did was first we added a feedback button to our web service, which you can see here. It gives you like a five-star feedback choice, and you can select like 5 stars or 1 star depending on how well it did. We found about 8 to 9% of our users actually gave us feedback, which is actually pretty good, all things considered. It's not that common for users to give feedback. We'd also like to know how well it's working when users don't give feedback. And luckily, there's a lot of kind of implicit signals that you can use to tell whether the agent is doing a good job or not. For instance, is the user getting angry at the agent? Or is the user saying positive sentiment things? Or are tests passing? Did it make a pull request to GitHub? Other things like this. And so we also trained a feature-based regressor where we extract a whole bunch of features, and we try to predict like what the feedback would have been for that to some positive effect. And so this allows us to do some interesting things. Like we were able to compare how well different language models worked, how important it is to show users plans of what the agent is doing, and also how important is it to have really long-term memory in the agent. And we found some interesting things. So like the first thing is when we moved from GPT 3.7 to, Claude 3.7 to Claude 4, we found a notable improvement in how much our users like the outputs. When we moved from Claude 4 to GPT 5, we found a notable decrease in how much people like the outputs. And this is interesting. The reason why it's interesting is because if we looked at the benchmarking results, we were able to notice that Claude 3 versus GPT-5, Claude 4 versus GPT-5, on some of the benchmarks that corresponded to the tasks that the humans were actually doing, was actually kind of a wash. Like GPT-5 was really good at benchmarks. Claude 4 was also really good at benchmarks. So it was kind of like they were both pretty good. But on the other hand, GPT-5 was kind of like notably worse with respect to human output. Does anyone have an idea why this might be? Any guesses that are about what our benchmarks are not catching? Okay. If I've stumped everybody, number one, GPT-5 was really slow. And users like fast language models. So that was number one. Number two, GPT-5 was not very verbose. Claude would give frequent updates about what it was doing, where GPT-5 would just work for a long time and then report back. And you might know some engineers who do similar things. You know, they work for a really long time and then they come report back. And then you might know some engineers who also give you a lot of feedback. And too much feedback is also probably a problem, but there's that. Another thing that I think is a really big problem right now is handling underspecificity. And what I mean by underspecificity is, like as was mentioned this morning, it's very rare to know what you want in the first place. And every single query you put into an agent is going to be underspecified in some way. So just to give an example, the query that I put in the agent here was tell me about the MIT AI encoding event today and create a site with all the speakers and their profile photos. I didn't say anything about the color scheme or what web framework it should implement it in. And it did fine, I guess. I actually don't even know what web framework it implemented it in, but the site looked pretty good to me, so that's maybe fine. But there are other things that you really don't want. You don't want it to make a mistake on. Like you don't want it to delete tests in your repo that are not working or other stuff like that. And if you give underspecified instructions, it will also make a lot of mistakes. So it's a really tricky problem. So how do we start working on this problem? The way we started working on this problem was we created a benchmark where essentially we took SweBench Verified. And what SweBench Verified is it's a version of SweBench where people at OpenAI basically went in and manually had a whole bunch of software developers look and say, okay, this GitHub issue is solvable just from the issue description. There's not significant ambiguity in here. And we redacted a lot of the useful information and came up with a vague version of SWE-bench that didn't have all of that information. And then we gave the model a tool with which it could interact with a user and ask questions. And so what we found is if we take the fully specified version of SWE-bench from SWE-bench verified, it did a pretty good job. It got 50% of the issues correct with an older language model. When we redacted the information, it only got 24% of the issues correct. And when we allowed it to ask questions, it got 39% of the issues correct. And so it was able to close some of the gap, but not all of it. And ideally, it should be able to close all of it because the underlying information is accessible if it could ask the right questions. So then another question is, could we train models to actually be better at doing this? And so one interesting thing nowadays is, as I mentioned in the part where I was talking about rollouts, we can do rollouts with, in reinforcement learning, if we have just inputs and we have a validator that gives you a reward. And so what this also means is if you can evaluate it and then you can scale your evaluation to be really large, you can also train your models because your evaluation is essentially like, it's a reinforcement, it can become a reinforcement learning environment. And so what we did is we essentially did exactly this. So we created a larger version of this based on SWE-gem, SWE-Smith, R2E bench, and other existing reinforcement learning environments with well-specified issues. We created the vague prompt. We created a user simulator. We also gave the user simulator preferences about what types of solutions it liked. And we gave an effort rating for asking questions. So every time it asked a low effort question that was easy to answer, it would get a small negative reward for bugging the user a little. If it asked a higher effort question that was harder to answer, it would get a large negative reward for for bugging the user and causing them to ask a lot of questions. And I think we got some really exciting results. So we trained basically a 30 billion parameter model. And we were able to exceed GPT-5 from the point of view of our evaluations based on how well it did and how good it was at asking low effort questions pretty significantly, both with respect to task success and the kind of like productivity and personalization scores, or proactivity and personalization scores. And we also see some interesting dynamics where it starts asking questions, or it starts out not asking many questions. It ramps up to asking more questions, including medium effort questions. And then as it gets to the end, it's asking lots of low effort questions and very few medium to high effort questions. So it was able to kind of distinguish between these various questions. And one criticism of this is our user simulator is not perfect. Maybe these would actually bug users a lot or something like that. But then we can improve our user simulator and kind of fix that. So a final thing I'd like to talk about is agents that adapt with us. I'll kind of jump through this. But one big trend in the past few months with respect to agents is everybody is kind of standardizing around the idea of skills. And skills, as I mentioned before, are basically ways to plug in new information into an existing agent to allow it to be better at doing certain things. We have a series of papers, or my student Zora Wang has a series of papers on automatically inducing these skills. And the first one, called Agent Workflow Memory, which came out last year, basically the idea is you utilize some of the things, or run tasks through the agent. You get the agent trajectory. You have essentially a critic that decides whether you did a good job at solving the task. And if the critic says, yes, this task was solved well, this could correspond to our feedback predictor that I talked about before. You then induce workflows by throwing the trajectory into a language model and asking it to split it up into workflows, naming the workflows, and providing these to an agent. And this is pretty interesting because we tested this on web browsing tasks. And essentially what you can see is that as the agent does more and more tasks, it just gets better and better at utilizing these workflows. It learns more about the task domain, and you can get a gap of up to 15 points on how successful it is at solving the various tasks. Another interesting thing you can see is as the tasks evolve, they get more and more complex because the agent becomes better at solving more complex tasks. So it can kind of build upon its previous ideas. Then we had a follow-up paper that we just presented at Column last year, which is we essentially called this agent skill induction. And the idea is instead of feeding in raw agent trajectories, we actually allow it to come up with programs. And what the programs do is, again, we did this for web browsing GUI-based tasks. It will do things like come up with a search review program that will do things like fill a search box ID and click the search button ID, or opening the marketing reviews where it clicks to marketing, then it clicks to all reviews. And this has a few benefits. Number one, it allows you to actually test them. You can rerun them on the website to make sure that they work properly. Another thing is you can come up with very compositional programs. So you could have one that does a for loop, which is like rate all products, where you feed in a list of products and it will rate all of the products and just click through the thing without doing another agent, the website without doing another agent call. And we demonstrated that this both improves accuracy and improves efficiency with respect to how you use agents. I'm pretty excited about this because, as I talked about before, there's an idea of clicking versus coding. And so what this means is even if we have an interface where we're forced into clicking, where there's no good API for it, we can create an API. This is a way to create an API for it. And sure, the API works by clicking on a website through a browser that's not super efficient. It might not give you the nice abstractions that you would have with a typical API. But let's say you have legacy software that nobody is going to update or create an API for. It gives you an option to do that. So what I'd like to conclude about is I talked about a lot of stuff we've already done. And we haven't solved these problems, but we've made progress on them. What are some big problems that we're thinking about now? So the first one is the verification bottleneck. So this is a thing that a lot of people are talking about now. Basically, code is so cheap that it's nearly free. And so we can generate lots and lots of code. The problem is good code is not cheap because you need to review it, you need to make sure it actually works, and other things like this. And we have a few tools at our disposal. I mentioned a little bit about skills and how people are using skills. One thing is that because agents can do a lot of things, agents can also help you with verification. So one of my favorite skills that we have is this code review roasted skill, and it basically says, give a brutally honest code review in the style of Linus Torvalds. And you should have good taste, never break user space, pragmatism, and simplicity. And so basically what this will do is this will take your horribly verbose, horribly long, AI written pull request and criticize it. And then you can ask the agent to go in and say, OK, fix all of the problems it pointed out. And with recent language models, this actually works pretty well. I also mentioned this a little bit in one of my questions this morning, which is there's recently Factory AI, another agent company, came out with kind of a readiness report for how ready a code base is to have agents used on it. And basically, the idea is that you should have certain things set up in your code base to very quickly catch bugs when AI causes sorts of issues. So you should have static analysis. You should have CI set up. You should have testing with unit integration and coverage tests. You should have documentation like agents.md, which is kind of like a default skill for the repository. And you should have environment templates, logging, tracing, and metrics, code owners, issue templates, and sorts of stuff like this. And so these are just good software engineering practices, but agents can follow good software engineering practices if you tell them to do so. And so essentially, this readiness report skill will tell you if a repo is ready to have agents used on them. Another thing that I'd like to point out that we're thinking about a lot is large code bases. So this is how can you break down a large code base and handle individual parts separately? How can you prevent agents from getting lost in them, have good localization? Realistic and diverse evaluation environments is still a problem. Like, let's say we want to start applying to scientific tasks. Do we have good environments for scientific coding? And also scaling them. So once we have evaluation, can we scale these up for reinforcement learning-based training? So if any of this is interesting, I'm happy to talk more about it. You can also take a look at our code and use it yourself if you want to.
Thank you.
Yeah.